So I wanted to talk to you one more time about the t-distribution. We worked an example in class where when we were looking at the distribution, the very first thing we did was verify its normality and if there were any outliers. And we did that using both the QQ plot and then a box plot looking for outliers. Now let me show you kind of why we needed to do that. Here I have an applet that's talking about a set of data that is skewed right. And so what happens to my t-distribution or my t-interval whenever we have data that's not normally distributed? That's what we want to look at for just a second. So let's say that I want to talk about a 90%, 95% confidence interval. And I know that my data is skewed right, and I'm talking about a really small sample size of 5. So if I look at 1,000 of these intervals, here is just a simulation. Notice that my confidence interval, this right here says that I should have 95% of these intervals that contain my, my standard deviation. Now look what percent is actually containing, not my standard deviation, but my mean. This is the proportion of intervals that actually contain my mean of mu. So only 0.88 or 89% of the intervals actually contained the population proportion. Now, what if we do this again, and this time I want to look at it, and I want instead, I'm going to increase the sample size. So the previous one we were just looking at was talking about a sample size of only 5. Now, what happens if I look at 1,000 intervals of size 10? How many of those contain my population mean? Again, we wanted a confidence interval of 0.95 or 95%. I am a little bit closer here at 0.895, so I am just a smidge closer, but I still have more intervals. The proportion of my intervals that do not contain my 50 is still greater than my confidence interval that we wanted. Now let's try this again, only let's talk about it with 20. Let's do a sample size of 20. And you can see that the proportion of intervals that actually contain my mean, which is what we're looking at when we talk about a confidence interval, has grown to now 0.931. While this size of sample still does not contain my my mean like I want it to, right? We want 0.95 of them, 95% of those intervals to contain it, and I'm still only at 0.931. You can see, however, that when my data is skewed right, I'm going to have to be increasing the size of my sample. And that's one way for us to be able to get the proportion mean, or whatever mean we happen to be talking about, to be within my level of confidence. And so the t-distribution, or the t-interval that we're looking at, it becomes really important then for us to take the data that we're given, because we're talking about a sample distribution, right? And my sample distributions, we don't always know whether or not they are going to always follow a normal distribution. So one of the checks that you want to make is, does the data that we're looking at, the sample distribution that we're looking at, like we did in class with the pennies, we want to check the QQ plot, and then we also want to check the box plot to look for outliers, because remember, the sample is not resistant to outliers. And what happens then if you do happen to come upon a distribution where you just can't get it, the model fails. You can't get the size to be great enough for your distribution to become normal, then you have two other options for us to do. One's called a non-parametric procedure, and one is called bootstrapping. And you're just not going to do that in this class. So all of the distributions that you're going to end up looking at for the t-interval in this particular class will be something that leads you more in a normal distribution, but be aware that there's other methods in case this model fails on our t-distribution.